All right, so we're going to take a look at the relationship between Gibbs free energy and pressure of a system. So we know that the enthalpy is not dependent on the system, but the entropy is. Enthalpy is just heat change, but delta S is entropy change. So why would that be dependent on the pressure? Well, remember about positional entropy, that the more positions particles can occupy, the higher the entropy is. And so if you increase or decrease the pressure, you're giving those particles more places to be. Since delta G is dependent on both delta H and delta S, it's also going to be dependent on pressure because delta S is dependent on pressure. Okay? If you're not at 1 atmosphere, that would be non-standard states, then you don't use the little degree sign. And you'll have to calculate delta G if you are not at a pressure of 1 atmosphere, as long as it's a pure substance. Okay? And this is a relationship. Delta G without the degree sign, that's non-standard. That means not at a pressure of 1 atmosphere, for example. But that's equal to the standard delta G plus a term that includes pressure. RT, gas law constant, times the temperature, times the natural log of the pressure. Okay? So delta G is change in free energy at 1 atmosphere, and delta G is the change in free energy at whatever pressure P is. So they're related. You just have to adjust the standard delta G by this term, RT, natural log of P. So we can also determine the non-standard delta G for a chemical reaction if we use the reaction quotient, Q. Okay, it's very similar. So the non-standard delta G is equal to standard delta G plus RT times the natural log of Q. Okay, Q is the reaction quotient. Remember, it's calculated like an equilibrium constant. It can either be in pressures or concentrations, depending on what you're given. Okay, we use the 8.314 joules per mole Kelvin because we're dealing with delta G, which is energy, Gibbs free energy. So that's an easy way to remember which R value to use. Okay, so here's an example. We want to find the non-standard Gibbs free energy for the reaction of carbon monoxide and hydrogen to form methanol, methyl alcohol. Okay, the temperature is going to happen at 25 C, but we have carbon monoxide at a pressure of 5 atmospheres and H2 at a pressure of 3 atmospheres, and we want to find the overall delta G for the reaction. So the first thing we have to do is find the standard delta G value. We can go into Appendix 4 and we can get the product and reactant values for delta GF. And since we're given pressures, we can calculate Q from the partial pressures of those gases. Remember that CH3OH is a liquid, it's a pure liquid, so it's not going to show up in your calculation or your expression for Q. Okay, so we can go and look up our delta GF values, and delta G is similar to delta H in a lot of ways, and one of those ways is that if you have an element, the delta G value is going to be 0. Okay, but carbon monoxide has a negative delta G value, and so does methanol. We plug that into our summation, and we get that delta G standard is negative 29 kilojoules. Okay, our Q is going to be 1 over partial pressure of carbon monoxide times partial pressure of H2 squared. Notice that there's nothing in the numerator except a 1 because methanol is a pure liquid. It doesn't show up in equilibrium constant calculations. So we get our Q value of 2.2 times 10 to the minus 2. We have our delta G standard. We plug that into our expression. Delta G is equal to delta G standard. We're going to want to put everything in joules because we're working with R, whose value is in joules. Plus R times T, T is 298 kelvins, times the natural log of Q, which is natural log of 2.2 times 10 to the minus 2. And delta G is going to be negative 3.8 times 10 to the 4th joules, or negative 38 kilojoules per mole. That's the non-standard delta G for this reaction. Okay, standard delta G was negative 29, but when we do this at a higher pressure, it becomes more spontaneous. So this is a reaction that responds to pressure in a positive way. It actually causes the reaction to shift to the right because it becomes more spontaneous. It's more negative at high pressure. Well, that should make sense, right? Under high pressure, you've got 2 moles of gas. On the right, you have no moles of gas, lots and lots of room for for molecules to exist. So it would make sense that if you increase the pressure, you'd shift that reaction well over there to the right. So what does delta G without the degree sign, the non-standard delta G, mean? Okay, if you have a negative value for that delta G, it means the reaction lies to the left at equilibrium. Okay, the system contains mostly products at equilibrium. Well, what about at equilibrium now? Let's take a look at free energy and equilibrium. Okay, so we know that at equilibrium you have a constant K that determines where the equilibrium is going to happen. And it doesn't matter how much of the reactants or products are initially mixed, you'll always come to this equilibrium position at a given set of conditions, primarily pressure and temperature. Okay. What do we know about delta G at equilibrium? What is it equal to? 0. Q at equilibrium is K. So we can substitute delta G at equilibrium 0 and Q with K, and then rearrange, and we get our standard delta G is equal to negative RT natural log of K for equilibrium conditions. Okay? If delta G standard is equal to 0 and K is equal to 1, then the delta G of reactants, so that the Gibbs free energy of reactants is equal to the Gibbs free energy of products. At equilibrium, neither reactants or products are favored. If delta G is less than 0, in other words negative, K is greater than 1, the G of reactants is greater than the G of products. Products are favored. And if delta G is positive or K is less than 1, then we favor reactants. This is just a summary of how these things all work together. Okay? Here's an example. Nitrogen and hydrogen gases combining to form ammonia. The delta G standard value is negative 33.3 kilojoules per mole. We want to figure out which way will this reaction shift if we do the following. So the partial pressure is 1 atmosphere for NH3. The partial pressure of N2 is 1.47. The partial pressure of H2 is 0.0100. First, let's figure out what Q is. Plug into your Q expression. We find out that Q is equal to 6.80 times 10 to the 5th. Now, I don't have a K value to compare this to. Okay, but if I use the expression that I already learned, delta G standard plus RT natural log of Q, I get a delta G value of 0. This reaction with those pressures is at equilibrium. Okay, so there's no shift. Well, what if I have these pressures? 1 atmosphere, 1 atmosphere, and 1 atmosphere. Which way will the reaction shift if I do that? Calculate Q again. Q is 1. Delta G is negative 33.3 times 10 to the 3rd joules. That's the standard. Plus RT natural log of 1. Natural log of 1, okay, we have 0. So delta G is negative 33.3 times 10 to the 3rd joules. Because natural log of 1 is 0. It takes that term right out of it. Pressures are all 1 atmosphere, so we're still at standard states. So we could have done this without a calculation if we remembered that at standard states, where all gases are at 1 atmosphere, delta G is equal to delta G standard. Okay, but it's negative. So K is greater than 1, and that means that we're going to shift to the right and create more products. Okay, so we know that delta G standard is equal to negative RT times the natural log of K. That's at equilibrium, right? And delta G standard is also equal to delta H minus T delta S. So we can kind of rearrange this relationship here. And we can figure out that the natural log of K is equal to negative delta H over RT plus delta S over R. If we plot k, natural log of k versus 1 over t, we'll have a linear graph, okay? The slope of that graph will be related to the enthalpy of reaction. It's very similar to types of graphs we've seen before with kinetics and with equilibrium. It's the same kind of thing. You know, in chemistry, if you can get an expression, a relationship into a y equals mx plus b form, and you can get a straight line, the slope is always going to be something important. And so in this case, the slope is related to, is proportional to the enthalpy of reaction. Okay? And the place where it crosses the y-axis, the intercept, is proportional to the entropy. Just have to divide by r, or multiply by r. Finally, we want to do work with this free energy. Okay? We can calculate the amount of work that can be done. Work, the maximum amount of work, is what delta G is. Delta G is the capacity to do work. It's energy available to do work. So if the delta G value is positive, then that means you have to do work on the system to make the process happen. Okay? You can never get to the maximum work because there's always going to be wasted energy. Energy is lost all over the place. It's the nature of energy and this universe that we're in. So you'll never ever be able to achieve the maximum work, but you know, depending on how you design a system, and that's what engineers do, is try to figure out ways of designing systems where you can maximize the amount of work and lose as little energy as possible. The important thing to remember, though, is that's what delta G is. Delta G is the maximum amount of work that could be done with energy from a reaction that's not being used to do something in the reaction.